Let me introduce you to today's guest speaker, Sean Ryan, who is the Marine Energy Testing Manager at PacWave, who will share with us testing wave energy for the future, an update on PacWave South. A little bit of background on Sean is he has a BS from Texas A&M in marine science and an MS from the University of South Carolina in geological sciences. He's worked offshore for most of his career, either on UNOLS vessels or seismic survey vessels. Sean's focus has been acoustic physics, but has worn the hat of marine operations manager, geophysicist, petrophysicist, and rock physicist. Sean and his wife, Alex, moved his family from Thailand to Oregon in 2018 and have concluded that they could spend the rest of their days kayaking and hiking in this great state. All right, please join me in welcoming Sean.
All right, thank you very much. Thank you. All right. So I joined PacWave in March of this year. PacWave had worked with a number of people over the years to bring the project to where it stands today. And I have found through integrating with the different departments in the university that there seems to be a lot of knowledge gaps about who we are and what we're doing. So I'm going to try to cover some of that here today, and then take as many questions as possible. This is less researchy and more of an operational kind of report. So I don't know if it's live. There we go. Okay. So who are we? So we are part of Oregon State University. We are funded by the DOE, the Department of Energy, but we are also partnered with many of the national laboratories. We have a lot of different projects going on. All right, I'll let you work your magic. Yeah, I noticed my first slide was frozen.
Frozen.
I tried to keep it small.
Oh, let's see here. Close that up. Let's try this one more time. That work? Okay, so it's just a little bit of a lag.
Okay, all right. Okay, so we're working with the U.S. Department of Energy. Right now, I guess I could back up and just mention that, the kind of people that we're working with. This is a test center, not a research organization or a lab. So our function in the university is kind of odd, different than what most would expect. But the idea here is that we are facilitating the different kind of researchers that are building devices to put offshore. And we're kind of the last step before commercialization, before reaching the open ocean. And so these people that have developed their methods, and believe me, there are a myriad of methods on how you can create electricity from waves. Pretty much the last step of that process is to come here to PacWave. Okay, so we've had PacWave North, which I'm not really going to talk about, but that is a site that has been here open and running. That's right off of the Yaquina Head area, and it is still available for use. It is not grid connected. Essentially, we deploy scale devices or other, meaning smaller devices than an open ocean device out there. It's been used in the past, but it doesn't have any permitting. One of the great things that we've led to in this process is that we've taken care of all the permitting issues related to putting a device offshore for a number of years in PacWave South. So PacWave South is pre-permitted. All right, so here's a simple cartoon kind of showing the idea behind it. There's a lot of inaccuracies and there's no real anchors or moorings and stuff. So it's missing a lot of detail, but it kind of shows you some essential devices that are being used elsewhere or possibly that we would test here. We have different kinds of overturning devices. We have, there's the Wello device that's up on the right-hand side there that essentially has a huge counterweight on the inside of it. And I think you should kind of keep it in your mind that if you've seen testing of devices in the past, they do testing at Hinsdale Wave Tank, and those devices are on much, much smaller scale than what we're talking about here. So the size of these devices, they can range, but they could be 50 feet, they could be 600 feet. So all kinds of different sizes. But the idea here is that we are connected to shore. We're in the process of putting in cables and all the infrastructure that goes around that. So I'll step through that. Okay, so this is a simple map to show you the location of where PacWave North is and PacWave South. You can see the approximate location of where those cables are going to lie heading out from the shore. They come ashore down by Driftwood State Park, which is just south of Seal Rock. And I'll talk more about what we've done up till now and what we're working on this summer there. So this is something of a timeline. This is a lot of information, but let me just kind of point you to these color scale at the very bottom and essentially show that it's been 12 years since the original feasibility study. So the preliminary design is kind of in that golden color, and then the blue section, which is the years in between, is the permitting. And so that's all been taken care of up till now. And that's where we got our FERC licenses and our BOEM lease. And now we are in the red section at the end, obviously, 2023. And I'll go over what we've done so far. Okay, so these three pictures on top of here are kind of showing you three different things. So the top right picture is the underground construction, which involved actually using a boring technology to put 4 conduits up to 1 mile offshore, where they puncture through the subsurface into the water column. And they were just capped at that time when they were put in and then filled with nitrogen. And they've been sitting there since they completed that project. And then just about a half mile, I believe, down the road from Driftwood Park, which is where those cables will come ashore. We're building the utility connection and monitoring facility. It's currently underway. It's 3 buildings. One is nearing, it's up to the 2x4 stage. The other ones we're just laying the foundations for. So those buildings should be ready in 2024, but the site will become fully functional in 2025 when we actually get all the electrical gear, which is the electrical switch gear, which makes us able to put our power onto the grid. Okay, and the cable laying that I just mentioned earlier, we will have a ship very similar to this one here. I believe this one is in Europe, but essentially a cable laying vessel that will be offshore next year, 2024, the summer. You will see it just like you can see our vessel that is out there today. It's actually probably dropping anchors right now. So we will be laying the cable and attaching the connectors that we will lay at the bottom of the ocean that will sit there until we have a client arrive to connect to that connector. We will bring it up off the bottom floor and then attach the umbilical to their device. So, all right, so here we go into the construction. This phase has been completed. Again, these are the tracks for the 4 conduits that were put out there. These conduits it's a steel casing. It's about a 9-inch inside diameter, and it's pretty common off-the-shelf equipment. And so those are the subsea conduits. And then from there, they turned those boring rigs around and then drilled to our UCMF site where we're building our energy conditioning equipment, which is that red block that you see in the lower right-hand corner. And we dug what we call the terrestrial conduits. This is just showing you what we were doing for that bore path. This is a map of the shear velocities, so we can determine the stiffness of the rock and essentially its reflectivity and stuff. So the idea was to get into the basement rock, and that's what you see in red. And so we were boring from the right-hand side down into the red section with the highest shear velocities. And then up here, we've punctured out of the seafloor in about 40 to 50 feet of water. Okay, this is what it looked like when they were doing the boring project. Here you can see that's the conduit with the tape measure. And it's a messy job, but necessary. It promotes the longevity of the project and how long the cables will last. And you know, it does borrow on an oil and gas technique, you know, which no one likes to think about, but it was very useful to use this technique. All right, and in the end, after all the boring had been done, we had built these what am I thinking of? The vaults. Thank you. I have a couple friends in the audience. So we have 4 vaults here. We originally had planned 5 cables, so we actually had 5 vaults built. But then we ended up deciding to cut back to the 4, so we have extra space. Possibly we'll rent it out someday. I don't know. But anyway, so these vaults both go to the subsea conduits and the terrestrial side conduits. We are right in the process today of opening these up so that we can access that, because we are about to start the process of clearing the nitrogen out of the conduits. We're going to have divers offshore, and we're prepping the whole system so that we can pull those cables through next year. All right, so this is just showing you that track again of how we dug the terrestrial side of the conduit. And is different. It doesn't use the steel casing, and it's high density polyethylene, and but the process, you can see the reason we had to take kind of a bit of an arc here was because we didn't want to drill under people's property that didn't want us drilling under their property. So I should mention that before that the site where we ended up putting PacWave South was decided by the fishermen. So our deputy director and project manager met with the local fishermen and basically sat in a town hall meeting with them and had them pick the location where it was best for us to build this site offshore, so that had the least impact on their fishing activities. So in the end, this is what the parking lot at Driftwood looks like. If you look kind of closely, you can see there are 5 manhole covers in about the middle of the parking lot. These are the manhole covers that go down into those vaults. And right now it doesn't look anything like this because we've just pulled them up this morning. So total, there's about 6.2 miles of conduit installed, both subsea and terrestrial. 1.3 million pounds of steel, and 60,000 pounds of high density polyethylene. And they closed that park for nearly a year. We're not closing it right now. You can still go out there and enjoy the beach. We just have the part around the vaults closed down for your safety. Okay, so moving on to the site preparation for the UCMF, which again is that utility connection monitoring facility. The design looks something like this. So OSU bought the property in yellow over here as its selection for the site. This is Wenger Lane that you can kind of see in this draft over here, and where the buildings will be located on Wenger. It's been under construction for a few months now, and it looks more like this. Actually, this is from about 2 months back as well. You can see that yellow pad over there is the vapor barrier for the foundation for the main control building. And then there's 2 other buildings. One is the conditioning building for electricity. That's where we'll have the medium voltage switchgear. And then the other is will be the 4 bays that go hand in hand with the 4 berths that we have offshore. That will be part of the PacWave site. The idea being that we would have 4 different researchers or developers out there with their wave energy converter devices. Okay, this is more what it looks like today. A big pile of dirt and more foundations. There's an amazing amount of grounding that goes into each of these buildings because we're going to be dealing with medium voltages, which is a little bit scary for most people. It takes a lot of extra certification and understanding for approaching and trying to work on anything that is in that area. Medium voltage might as well just be called high voltage. All right, and now going on to the cable prep work. To talk about the cables, RTC is RTKC. That is the company that OSU contracted with to design and work with us on the production of the cables and installation. Nexans is the company that is in Norway and Switzerland that we are working with to build the cables right now. They are currently under construction and they send us weekly photographs of what that looks like. It's about 50 miles worth of cable, so it takes a while to make. And right now with all the offshore wind, which is kind of choking up the supply chain for us, it gives longer lead times on all cable related things, because there's a lot of demand right now worldwide for cable. And then McCartney is the group we're working with out of Denmark that is building the actual connectors, which are very specialized, and we're very excited to see those come online. All right, this is just a quick rundown of Rognan in Norway, where the Nexans factory is. I just thought it was kind of interesting. The Rognan factory in that kind of top right picture is down towards the bottom of the photo. And then that yellow track is kind of an underground tunnel with a lot of wheels on it so that they can just spit the cable out at the factory, and it runs down this mile-long tunnel and then pops out at their port. And it'll look something like this. So it comes down off this this catwalk that you see here, and it comes down into these big reels, and they reel it out, and then they test it, and then they will reel it onto the ships off the side there. And so we're hoping to take delivery of that at the beginning of next year. There are two different kinds of cable that they're making. There's the subsea cable, which in the subsea, we're not as worried about temperature. So we can use kind of a smaller conductor. And so that's what you're seeing on the left-hand side. The copper in the middle there is smaller, so it can heat up, but it has lots of cooling as it's subsea. And then you see the shielding around it. That's to protect against EMF, which is always a concern. And then the terrestrial cable, which is on the right-hand side, we're using a thicker conductor because we are more worried about temperature. And so that relieves that pressure. And both have a multi-mode fiber optic 12-strand in duplex for communication, so that we can both communicate with the devices offshore, as well as we could send power to the device, or obviously we're hoping to get power from the device. And that is just kind of a rough sketch. They actually took a hacksaw to it so they could show us what it looked like inside. And then someone held all three together so we could kind of get an idea for what we'll be seeing when it shows up next year. And then these are the connectors from McCartney that I was discussing. These are three different versions. They all use the same technology. You can see the shielding on the umbilicals, and a lot of that is to maintain, you don't want to get a pinch point in these cables. They're very expensive. And so you want to keep a certain radius of curvature when you're winding up this. So you don't want to get below a certain radius, so that it doesn't put stress on those fibers. And we will be constantly testing the cables to make sure they're still functional. Usually it's just a test of the fiber optics, because the fiber optics will be the first thing that get ruined in any situation. Okay. And now I'm going to move on to what we're doing now. So our summer work. And this is the part that I was most interested in talking to you about. So the Seacor Lee is our vessel of the summer. We'll have two vessels next year. This boat came down to us from Anacortes yesterday and arrived this morning, and came into port around 8:30. So we were working with Starboard Maritime, and it's actually something of a storied history with this vessel. She was the command vessel for the cleanup of the Deepwater Horizon. So here she is this morning coming in, and then she docked down at the international terminal, and she's the largest vessel that's ever docked there at 265 feet. Now, this is a picture from Anacortes. That's her sister vessel, the other starboard vessel, the Ocean Guardian, which we will probably be using next year behind her. But what the picture is about is to look at the A-frame. She started out with a 10-ton A-frame, and we had her rebuilt to be 25 tons. So quite a substantial change. A lot of the work that we're planning on doing here is kind of constrained by the supply chain on the West Coast of the United States for large vessels. There aren't anchor handling vessels on the West Coast right now that can handle a lot of stuff that we plan to work with. But there's a lot of work right now going on with some of the larger commercial firms to remedy that situation, because there's a lot of planned wind, offshore wind projects in California that are going to need the same supply chain as us. So hopefully that will alleviate some of that pressure. All right, so using that vessel, the Seacor lead that I showed earlier that arrived this morning, one of the reasons it had to come to dock today was to put on the commercial dive team. And so they will be right off a Seal Rock, 1 mile offshore for about the next 3 weeks. They will be attaching a bell mouth to the end of our conduit, and it'll look something a lot like this. Our conduit actually pops out at an angle, so it's not horizontal like that, but it will look a lot like this. I think, oh, I didn't add that picture. All right, so yeah, this morning I did an inspection of the bell mouths, and I was going to add that, but I didn't. And then this is the other interesting work that will be going on this summer. We're doing a geotechnical survey. So after we leave our 4-point anchor off of Seal Rock, we will be heading along the cable route and performing these, it's called a cone penetrometer test, where it essentially is pushing a specific cone of a certain angle and size through the substrate. This is all being done with Matt Evans here at the engineering department of OSU. And from the pressure on the cone, the water pressure that's being detected around the cone, and then the friction along the actual staff itself, it uses those 3 terms, and it's able to derive certain properties of the substrate that will, can tell us it's essentially a soil test to tell us how strong, dense the substrate is. And this is very important to us for when we're going to be doing our trenching, because we are going to bury our cable next year. So that's very important for us to understand how we're going to trench, if there's anything we need to avoid, any shallow ancient reef structures, anything like that. And so we're going to be taking a lot of kind of shallow CPT samples all the way along the route. And then once we get down into the deep water where the PacWave South site is, which sits in about 80 meters of water, then we're going to be trying to take some much deeper ones. And at that point, the boat will come back into Newport Harbor, and we're going to put an extension on this. This is the Rosin 100, the device itself. And we'll be putting a big tower on the top of it so that it can handle a much longer staff, hopefully to get at least up to 10 meters of penetration into the subsurface. And then we'll be doing that all over our PacWave South site, which is 2 nautical miles by 1 nautical mile. And I believe our plan currently is to take about 20 measurements out there at hopefully 10 meters of depth. And I will be out there for that, so that's exciting. All right, and then also on board this vessel is an oceaneering ROV, and we don't have any plans to use it this summer, but we do have access to it, and it can be used in as a backup for any of the for the dive work that's going to be going on in the next 3 weeks. And I want to talk a little bit about some of the adjacent projects that are going on along with what we're doing here. So as we are supported by the DOE currently, but our plan is to become more of a commercial site where our funding will come straight from the developers instead of the government. We are constantly partnering with different groups so that we can advance the science, whether it's around safety, oceanography, engineering, and currently we have a couple projects in the queue. We're working with the DOE and NREL, the National Renewable Energy Lab out of Boulder, looking at a wave measurement study, comparing different ways of determining how much wave energy we have, what is the power spectrum of the wave climate here, and by using different devices, different kinds of wave buoys, ADCPs, things like that. So that's ongoing. We also have a constant acoustic monitoring planned for the next 25 years. That is the length of our lease with the government for this site. So we plan to have acoustic monitoring out there that whole time. That can be an amazing amount of data. It's terabytes of data. So we are working on the acoustic part with Joe Haxel, who used to be here, and he's at PNNL now. And then we're also monitoring all the mid-ocean information, like the wave buoys that I mentioned earlier, and sea states, conditions, weather, all that. And a lot of this plays into what the different companies, universities, groups that are creating these devices and that will be coming here to PacWave at OSU, they are going to want accreditation that their devices work. And they want to be able to prove that this is how their devices work. And then we're going to be able to say, well, look, these are the conditions that their device weathered this storm, and it's, it functioned just as expected. The different devices have different ways of working. Some of them, if a storm is coming, they will actually winch themselves down to the bottom and get out of the energy zone for self-protection. Other ones are, not as aware of what's going on around them, and will just be trying to weather out the big storms and stuff. So there's different ideas around that. And then we also have ongoing, again, for the next 25 years, environmental monitoring through Hatfield and Dr. Sarah Henkel, who's on our team and a huge asset. And then we're also trying to work with the local offshore supply chain here in Newport and Coos Bay, along the Oregon coast, and work with who we can. So if anyone here has any interest in that, or knows anyone that is kind of following that, I know it sounds kind of commercial, it's not very researchy, but a lot of the things that we're trying to do here can't be done without an active supply chain that is willing to support the kind of activity that we're talking about. As I mentioned, the huge anchors, some were almost every project that we have coming down our current pipeline has a research project around what kind of anchors they're going to be putting out. And so there's all kinds of different technologies. It has to be removable from our site. That's part of our licensing and permitting, is that anything we change on the seabed, we need to be able to take that back. We need to bring it back to its original environment. So that means that we can't use any cement. We can't use any products that would be left on the seafloor. We have to remove it all. So that has opened up a whole, and this is not just us, they're talking about the same thing in Massachusetts for offshore wind. And there are other test sites for marine energy in the United States, but it's all scale work. We're the only full-sized, grid-connected, full-scale test site. So a lot of people are looking to us to see what we're going to do to find a supply chain that works for what is a nascent industry here. Okay. So that pipeline that I talked about, currently we have 4 groups that we're working with, and this has come through grants through the Department of Energy. PacWave is fairly well known. They get a lot of publicity, and they're a great group to work out of. They're kind of associated with Berkeley, and that's their device on the lower right-hand side that they tested off the Scripps Pier last year. I believe it spent 11 months out at sea, but near shore. They had to manage their operations. Like when there were surfers around, they couldn't go out to look at their instrument because the surfers took precedence, and swimmers and all kinds of things. So, but very interesting project. The device that would come here, you can just imagine would be at least 5 times bigger than the one shown there. And then Sea Power, which has a local office. They're fairly well known in Corvallis. They have a device. This is a kind of a medium-sized device that's they're working to deploy off of Hawaii. And so again, you could kind of imagine 5 times that size, although scale is hard to determine from that photo, the device that they would be bringing here. And then we're working with Portland State and Aqua Harmonics to bring their device, which is the yellow one over here. And again, like I said, you can see just from these 3 examples that they're very different in how they're engaging with the waves to produce power. The PacWave just looks like a box. You know, how is that creating power from waves? Does that look efficient? But it's very technically interesting, and I really hope we get to see them here in 2025. And then Littoral Power is another one that we're working with. And so this is to kind of help you with that scale issue, since we've just been looking at smaller devices. I don't know how well you can pick up on these photos, but each one of them has like people in them or cars. And so you can kind of get something of a gauge. The Core Power, which is the one on the right lower, is a very popular European company that is currently deploying a number of devices off of Portugal. They're probably the most commercial of all the companies that are in this field. And then the one above them is the Wello. It looks something like a sailboat to me. And essentially it's got a very odd shaped hull that was designed to basically be very unstable. And so it would get extra motion from waves and really rock around. And then you have something of a counterweight inside that's spinning, and that spinning is creating electricity. And then the one on the left here is out of Ireland, but it was built in Portland at the Vigor shipyard. I believe this photo is from Vigor. I mean, you can see the size of it. So this is an interesting device because the idea, it's not about the motion of the device. It's huge. It looks, you know, twice the size of a ocean-sized barge. But it uses the waves come in a mouth on the front of the device, and the waves push air pressure up through a big turbine that creates electricity. And that turbine actually turns in both directions, so it gets it on the intake and the outtake. So it's creating electricity all the time. And so that is also currently in Hawaii, awaiting deployment there. And that is it for my slides for today. Again, my name is Sean Ryan. There's my contact details. And I'd love to talk to anyone that has an interest in wave energy, or Oregon supply chain for marine supply and services. Thank you.
All right, thank you. Do we have any questions in the room or online?
Hi, thank you for your talk. It was very interesting. I had a question about how, or if you guys connect with the Wave Lab that's also based out of OSU, or if you're different, then how do you differ from the Wave Lab?
Okay. Well, yes, we have a lot of dealings with Hinsdale. Pedro, who runs Hinsdale, is on most of our meetings with DOE and NREL and all that. So there is kind of a academic chain of how you would go from a concept of building a device, maybe a numerical model of some kind, or something in your pool out in the backyard, and how you would go from there to coming to a full offshore test site like PacWave, and that's called TEAMR. And so it's like a series of small grants that you can get through the government that will help you promote these ideas. And it has, kind of these way gates to see if your idea is good, and then if it's possible that it could advance the next stage. So the next stage may be going to a wave, actual test site like Hinsdale with a small device, something that you could put in a pool. And so he does a lot of testing. He's been doing that for years and years. So we're just now kind of coming in that we're kind of the end of that path. If they've passed through numerical modeling, and then they've built small devices, and then maybe a medium-sized device, and then maybe they've gone to Scripps, or there's a couple other places where you could actually go to open water, but it's for smaller size devices. Maybe it's shallower water, or the Great Lakes or something, and test your device there, and then possibly get funding for the next phase, which would be to come to a place like PacWave. Yeah. Sure.
Other questions?
Sorry, I have multiple.
Very good.
So when you were talking about the construction, and how you were contacting with fishermen on where was a good place for that, I was also curious as to how would this construction or the mechanism itself affect fishing or fisheries in general?
Okay. Well, so Sarah Henkel, the professor, integrated biology here, she has done a number of studies over the years to look at exactly that, the impacts on Dungeness crab, the effect on cetaceans. There's been a lot of other research that's been done looking at pinnipeds and pinniped pullout. What happens if a pinniped wants to pull out on a device that has a pinch point or something that could maim the animal, things like that. So these are all things that people are worried about. And if someone came to me with an idea and we could see well, that's an obvious problem, that thing closes and we don't want things that close. So yeah, there's a bunch of different points along the way where that would get picked up by the testing with DOE. They know that we can't allow certain devices. There are particular kinds of devices that we won't test here at all because we don't think it would be good for the biology. There's a particular device that's it's where the water comes in through the top and then comes down through a turbine, and that it seems like animals could get in there, and that doesn't sound like a good idea. So we're not permitted for that. We're not allowed to touch anything like that. Yeah, does that answer your question? Sure.
Questions online?
One of the questions asks, will information about the performance and fate of various WECs be proprietary, or will there be any provision requiring public disclosure of performance or incident reports? For example, if a WEC gets broken in a storm.
Right. So there is a certain period of time where certain data around their productivity is not public, but we are a public institution. So everything that we do here eventually makes it into the public record. So it will become public record at some point. Yeah, so now there are certain things that they may be monitoring that we're not monitoring, and they don't have to share that with us. But we do have the full spectrum of what the data that we're collecting on their device. And so that will be public.
Question asks, is there a plan to compare energy outcomes between pilots with the wave devices and wind turbines?
And wind turbines? Well, I wouldn't say there's a direct correlation there. The kind of the return, or what they essentially the cost per unit of electricity, of energy. I don't think that a wave device will ever hit parity with a wind device. But we have a lot of positive things that wind suffers with. We have a more constant train of energy through wave energy. And that, there are other components. We're testing wave here, but we're also part of the PMEC partnership, which ranges from OSU to UW and University of Alaska Fairbanks. And that is looking at all kinds of different marine energy, tidal, and others. There's a lot of locations that are more set up for a tidal device, which is essentially a turbine in the water. And then there are sites, obviously, like here. Alaska has a weird spectrum of both, right? That has some really high wave energy, some of the highest in the world. And it also has amazing tidal fluctuations. So it could actually do really well on both avenues. And so they're taking advantage of that. There's a lot of interest, especially for some of the more remote locations, and just trying to get villages off of diesel and stuff, which is currently what happens in a lot of those really remote locations, is diesel backup for any kind of electricity. So there's a lot of interest in that. And that's not really grid scale. What we're doing here is considered grid scale testing, which are giant devices. But there's no reason why you can't take a giant device that's proven itself and then scale it down and send it up to northern Alaska and to work there. So there's a lot of interest in that, and we've been pursuing that. Yeah.
One question asks if you can explain again about the penetrometer. Specifically, is it penetrating and testing the seafloor?
Yes. So there are two big wheels inside this device, and they have a certain friction coefficient against that rod that it's going to be pushing in. So it's kind of like just stabbing a sword into the ground. All right. Those two wheels, we know the friction between the rod and the wheels. They're spinning at a certain rate. And so from that, we can tell all the amount of pressure that's on that front cone, and then the amount of slippage along the shaft that's being inserted. So, and then we're also picking up the pressure around the cone for water pressure, which we also use for understanding exactly how connected the different layers of the sediment would be. So it's not a rock testing device. This is for sediments. It's a soil sampler. They use them terrestrially a lot for any kind of work. Anytime they're gonna put a road in a new area, they're gonna test the soils to figure out exactly how much grading they need to do and stuff like that. So they're using that same technology. They've kind of advanced it so that we can do it subsea. So this device is going to be sitting on the bottom, and then those two wheels are just going to start turning, and the penetrometer is moving very slow, maybe a centimeter per second or something, and as it's penetrating, getting that feedback on the friction of the device, and from that they can determine exactly how, like the bulk modulus, Poisson's ratio, and other deterministic properties of the soil. So
hi, Sean. Thanks for a great presentation. It's really fascinating. How many devices can be tested out there at any given time?
right.
And how long will the testing period for any given device last?
Right. Okay, so we have 4 berths out there, and the berths are a half nautical mile by 1 nautical mile. And really it's slated, we're only going to have 1 connection in each berth to a cable. So we can have 1 cable connected device in each berth. So that would be 4 devices out at one time. Or we could have more that kind of daisy chain off one if we're going to do an array. So we are permitted for up to 5 in each berth. So that's 20 total that could be out there if they're in array format. But right now we're mainly looking at who wants to be grid connected, who doesn't, because not everybody wants to have that grid connection. They're looking for some other aspect of research. And they might have their device out there, but then they want to power ROVs or other scientific devices and things. So there's a little bit of sway there. So then the question is, can we put 2 of them in 1 berth? I mean, if they're happy neighbors, why not? So, yeah.
Hi, Sean. Thanks for the great presentation. Couple of questions. You mentioned anchors.
Yes.
You've said you've got 4 berths, but the anchoring system is going to presumably be fairly extensive.
Yeah.
And you didn't really answer the question that was asked earlier about the effect on fishing in the area. I would imagine that fishing would be prohibited around some circumference of the actual area.
Right.
For safety reasons would be my anticipated. Is that accurate? And can you speak
so we
to
will,
the anchors or that?
Yeah, we will have we'll have corner markers so they can easily see. We also have local notice to mariners that tells them where we are. I don't know that they're prohibited from going inside the site. I assume that they chose that spot because it's not a favorite fishing ground. But they did have full weigh in on it. We tried to move it just because we're at a weird angle and our cables are extra long because of the angle that we're heading at. It's like 7 miles of cable instead of 5. And but they were like, no, that's good right there. So we're like, okay. As far as I mean, so there's drag potential. If they're going to be fishing right over the anchors, just like there's drag potential on any devices that are out there. We've had a number of buoys out there that have gotten hit by fishermen or picked up by fishermen. I think it'll be pretty open game. We're not out there, you know, to watch it 24/7, you know, but we'll have all the Coast Guard recommended safety precautions in place. And, you know, hopefully we don't run into too much issue with that. I think some of these devices will be very obvious where they are, others less so. You know, like I said, some of them have actually no surface expression, so they're all underwater. And so that would be very nice to have good buoys around it saying, hey, watch out, there's a big iron thing in the water here. Because we don't want any issues with the fishing fleet. You know, I mean, that's a primary resource around here. So does that cover that? Yeah.
Have any more questions? Okay, any online? Oh, okay.
One question asks, given that PacWave is located along the Cascadia subduction zone, what is the design criteria for large earthquakes and tsunamis?
Like I said, that has come into the planning stage of some of these devices. Like I said about the winching down, they can, some of the devices can actually pull themselves, maybe not all the way to the bottom, like to their anchors, but they can pull themselves a good distance down. I think their survivability is much greater in the 80 meters of water depth than right at the shoreline. So we don't have, you know, any facilities that are in the area. So we would project that if there were tsunami, we'd probably be one of the first power sources back up and running for Central Lincoln PUD. You know, we might not even ever go down. So.
And one more, what learnings from other wave energy pilots taking place elsewhere are contributing to your plans? Can you give an example?
Yeah, well, there are quite a few, actually. I was just reading last night about 20 different test sites in Europe. But the main one that comes to mind is EMEC, which is in Orkney, Scotland. And it is a premier test center that's been open for 20 years. So they've been doing what we're trying to do here for the last 20 years. And they've now gotten to the point where they're diversifying into hydrogen, creating hydrogen from wave energy, getting into offshore wind energy. They do a lot of tidal, which we're not going to be doing tidal energy here because we just don't have the resource for that here on the coast of Oregon. So we've been in close contact with EMEC, and we actually have a planned trip after our weather window because we're in the prime right now for offshore Oregon. And so we have plans for all summer offshore. And then as soon as that window closes towards the end of September, early October, we plan to head to Scotland and kind of do some tabletop exercises with them and some other work, you know, seeing how they do certain deployments and things like that. So we're hoping to learn a lot while we're there. But in the meantime, we've been doing a lot of stuff. We just met with them a couple months ago. They, yeah, I mean, we have weekly meetings with them as well. So Zoom is a great thing.
All right. And with that, please join me in thanking Sean for giving a great presentation today.
Thank you. Cheers. Long way. Never started.